So let's solve these problems on pressure, density, heat, and temperature. So for the first problem, we are given an air mattress that has these dimensions, and we are also given the mass of the air mattress. So first things first, let's find the weight of the mattress. That will just be m times g, which is 0.22 times 9.81. This comes out to 0.22 times 2.1582 newtons. Looking at our significant figures, there's two significant figures here. So I'm going to convert this into two significant figures. It's 2.2 newtons. All right, so next we'll look at the situation they are asking us about. So they are asking us for the maximum mass the mattress can support. So how much weight can the mattress support on top of this particular value? So let's draw the situation. If this is the surface of the water, the maximum weight supported by the mattress will be when it's completely submerged underwater. So this particular mattress, let's say it has a volume of V. The amount of fluid displaced will equal the volume of this mattress. So let's find that volume is equal to Vf is equal to 2.3 times 0.66. Now these two values are in meters, but this particular depth is in centimeters. So I will convert that into meters right here. And this value is 2.1252 meter cube. Looking at the significant figures, there are two significant figures, so I will convert this into 2.1 meter cube. All right, so in this situation, if I draw the free body diagram, I will have a buoyant force and the mass that this particular object is supporting. So if I call this M2, capital M is equal to M1, which is the mass of the mattress, plus M2. So looking at this free body diagram, the summation of forces is Fp minus capital Mg, and this should equal 0. So let's solve for this. We know that the buoyant force is equal to rho g Vf, which is the displaced volume, and we know that capital M is M1 plus M2 times G. Substituting the values, we know the density of water, so that's 1000 times, I'll keep G as G. We know Vf is 2.1 minus we know M1 is 0.22, so 0.22 plus M2 is the amount of mass supported, additional mass supported by the mattress, times G is equal to 0. Now G is common on both sides, so it gets in both these terms, so it gets cancelled. So what we are left with is 2100 minus 0.22 plus M2 is equal to 0. Solving for M2, I get bad. This becomes negative. Solving for M2, I should get 2099.78. There are only two significant figures here, but for now I think I'll just leave this as it is. So the question was, what is the maximum mass it can support in fresh water? This particular air mattress can support almost 2100 kg of weight. Right, moving on to the next question. Here the question is, on a flight, you look out the window. Suppose the air outside the window moves with a speed of 170 meters per second, and the air inside the plane is at atmospheric pressure. Find the pressure difference between the inside and outside of the window. So let me draw this situation real quick. This is, let's say, the plane window. We know that the inside pressure is P in, outside pressure is P out. And this is equal to P of the atmosphere. So looking at this particular situation, I can apply Bernoulli's principle and say that P1 plus half rho V1 squared plus rho g y1 is equal to P2 plus half rho V2 squared plus rho g y2. So here 1 is in, so P in. The inside air is not moving at any velocity, so it's 0. And y1, I'll just assume y1 is something. I'll just leave it as it is. I'll call it yn, or I'll just call it y. P out, there is a velocity v out, that's squared, and rho g, because these 2 points are at the same level, this side also will be at a height y. So this becomes 0. Rho gy is the same on both sides, so it gets cancelled out. In the part 1, we are asked to find the pressure difference. So P in minus P out is equal to half rho V out squared. Substituting the values, the density of air is 1.225 kg per meter square, meter cube. So we'll use that value times the velocity is 170 meters squared, meters per second squared. So after solving this, we get 17701.25 Newton per meter squared. Now this is part A. For part B, they ask if the window is a certain size, find the force exerted on the window by the air pressure. So let's draw that situation again. This is the window. So because of the internal pressure, there will be a certain amount of pressure, let's call it Fn. And because of the external pressure, there will be a certain amount of force on it, let's call it F out. So looking at the summation of forces in this case, towards right is positive, so F out minus F in, but F is equal to P pressure times area. So my summation of forces is equal to pressure on the outside times area. The area is for this particular window minus Pn times area. Now because this particular window is not moving, the summation of forces is equal to 0. So P out minus Pn times area is equal to 0. We, for a fact, know Pn minus P out. So taking the negative outside, we get Pn minus P out times area is equal to 0. So substituting the values 7701.25. The area is just these two values multiplied together. So 25 multiplied by 42. But these two are in centimeters, so I'll convert them into meters. This is equal to 0. Actually, this is not equal to 0. This is equal to F net. Pardon the error, because we are not told that this is an equilibrium. After I calculate this entire thing, I should get F net is equal to negative 1858.63 newtons. So that just means the net force is in the negative direction. So it's pushing the window outside. All right, next question. Here we are given the amount of heat added to a 101 gram piece of aluminium at 20.5 degrees Celsius. So first things, let's look at our specific heat. We have the specific heat in Kelvin. So we should convert the degree Celsius to Kelvin. So T initial is equal to 20.5 degrees Celsius, which is equal to 20.5 plus 273 Kelvin. So the temperature is 293.5 Kelvin. All right, so the formula for specific heat is the amount of heat energy added divided by the mass times the change in temperature. So for our case, C aluminium is Q, heat energy, divided by the mass times T final minus T initial. All we have to do is convert this equation to be in a form of T final. So the way I will do that is by multiplying aluminum with TF, and I'll open this up as well. So C aluminium times M times Ti is equal to Q. So TF is equal to Q plus C aluminium times mass times Ti divided by C aluminium times mass times, that's it. So the value of Q is 72.3 joules multiplied by 1050 multiplied by 101 grams is 101 divided by 1000 multiplied by T initial is 293.5. Divide this by 1050. Right. So when you solve this, you should get a value somewhat close to 294.182 Kelvin. Now you can leave this as it is because we are not explicitly told to find the value, the temperature value in Celsius, but I will convert this in degrees Celsius. 24.182 Kelvin is equal to 21.8 degrees Celsius. So the initial temperature was 20.5 degrees Celsius, and the final temperature after adding 72.3 joules of heat is 21.18 degrees Celsius. Right, moving on. We're given that a water tank springs a leak that is 2.9 meters below. So let's draw that situation. If this is my water tank and this is the level of water, let's say the leak is somewhere around here. So we know that this height is 2.9 meters. The leak is open to the atmosphere, so there's P atmosphere on the top here, and as the water leaks out, there is P atmosphere pressure at that leak as well. So looking at Bernoulli's principle, how about we set our point 1 on the surface of the water and the point 2 right as the water is coming out of the leak. So P1 plus half rho V1 square plus rho G Y1 is equal to P2 plus half rho V2 squared plus rho G Y2. Alright, so looking at P1, the amount of pressure at the surface of the water is P atmosphere. The velocity at that point is 0, and considering this as my 0 point, the height here is 2.9. So rho G 2.9. P2 is again P atmosphere. The velocity is something, it's not 0, so I'll leave it at V2 squared, plus the height here is 0, as we considered the height at point 1 to be 2.9 meters. The height at point 0, this point where the leak is, will be 0. So that's 0. So that gets cancelled because it's multiplied by 0, and that gets cancelled because it's multiplied by 0. P atmosphere is the same on both sides, so those get cancelled too. So in the end, what we are left with is rho G 2.9 is equal to half rho V2 squared. Rho and rho are the same, so again we will move things around. 2G times 2.9, which is equal to we're finding V2, so 2G times 2.9 under root is equal to 2 times 9.81 times 2.9. That is 56.898. The value I get when I square root it is 7.54 meters per second. So that is how fast the water is moving out of this particular leak.